Hey guys, Mr. Lashur here. Looking through positive physics. We're on a free fall problem set. This is problem number 2 from complete problem set 3. We have a student fires a cannonball vertically upwards. Alright, so we want to identify vertically upwards. The cannonball returns to ground. You need to think what that means. After 4.4 second flight. We need to determine all unknowns and answer the following questions. We can neglect drag and the initial height and horizontal motion of the cannonball. You can see here we have the solutions already for you. I'll show you how I arrived at those now. So first attempt we're going to do is we want to actually go through and set up a table of our kinematic variables. We know we want to look for a distance probably, maybe initial velocity, a final velocity, a time interval t, and then our acceleration. Right. So we're not given much information in this problem. What we do see though is we have a delta t of 4.4 seconds. We know the acceleration in this problem is going to be gravity. It is a free fall problem, so I'm going to mark that as 10 meters per second squared. We don't have anything else though, so where do we begin on a problem like this? Well, the nice thing about free fall problems is that we know things under acceleration, constant uniform acceleration, are parabolic in nature, and there is a symmetry to a parabola. So if we go over to the left here, we can see the parabolas here for you. I'm going to look at the very top of this parabola, and I'm going to draw a line straight down to the ground. If you recall our conversations from class, we know that when we throw a ball straight up, its maximum velocity is right at launch, so that's VO, and as it goes up, gravity is going to act down on it, right? And that gravity is 10 meters per second squared. So the entire time that ball is going up, the ball is slowing and slowing and slowing and slowing and slowing until it eventually reaches its highest point at the apex of the parabola. So we know something about this point. We know that here the velocity is equal to 0, right? And what happens as it starts to come back down? Remember, gravity is going to be accelerating it now in the down direction. And what we see is that every single point here, it's going to have the same exact velocity as it did on the flight up, except now that velocity vector is going to be negative. So VF. And if we can look at exactly where it was launched from, that velocity should be the exact same velocity that it was launched with. So the final velocity is equal to the final velocity is equal to the original velocity, but in the negative or down direction. So let's just kind of think of a frame of reference here. We should always draw this in. I'm going to draw my frame like this, and we're going to have the x direction and the y direction. We'll call this way up positive and this way positive. Now, for this problem, we can ignore the horizontal. I don't need to worry about the x. I'm just going to look at the y direction. So if y we're calling up, that means that our gravity is going to be negative. So this will be a negative 10, because gravity is going to be acting down. So where do we want to begin with this? Well, with the symmetry, we see at the very top here, v equals 0, right? So if it took 4.4 seconds total in order to travel its entire distance, that means at its highest point, t must be equal to 2.2 seconds for the halfway point, half of the flight. All right, that's good. So now with this 2.2, we're actually going to split this into two problems. We're going to look at the top of the parabola, and we're going to track its path all the way down to this final position here. Okay? Let's look at our kinematic equations. We're going to go VF equals VO plus AT. All right? And if I look now, if my VO is 0 meters per second at the halfway point, we can set this as our initial speed and solve for the final speed as it travels its path down to the ground. So let's plug in some numbers here. We'll have VF equals 0 meters per second plus, we're going to do negative 10 meters per second squared, thanks to the gravity, times the time interval. Well, this is only half the path, so I'm going to use that half time interval, 2.2 seconds. right? And you should be able to see with the 0 here, plus a negative 10 times a 2.2, we see that velocity final is equal to negative 22 meters per second. All right, so we'll put that number up here, 22 meters per second. The negative sign that you see here, right, this little negative sign, that's only telling us that that velocity is in the down direction based on our frame of reference. So we don't need to worry about that because we only were looking for its speed. You can see we've got the 22 here. That 2.2 came from the symmetry of the parabola, no real math required. But now we need to figure out its maximum height, okay? So we're gonna use the same approach. We know that at the highest point, its velocity is 0. We now have a final speed. Because of this relationship here, we know that if it was final speed is 22 meters per second, it must have been launched at that same speed, but in the positive direction. So let's kind of approach that using the same logic. We have a relationship that says d is equal to VOT plus 1/2 AT squared. The nice thing is that when our original velocity is 0, right, we can cancel some terms out. So if we think about the original velocity from the top of the parabola as 0, we can rewrite this equation as 1/2 AT squared because this whole expression will cancel out. Right, so boom, that's when v equals 0. Right, so this only works when our initial velocity is 0. Now, given that, we can figure out the distance it traveled under that acceleration for the same time interval. So that's good. Let's plug those numbers in. We'll see that we went, I'll do this in a different color for you. How about go back to this green. I'm going to scroll down a little bit. We have that d is equal to 1/2 times, down we're calling negative 10 meters per second squared times the time interval. This is still from the top of the parabola to the bottom, so I'll do the 2.2 seconds squared. All right, and let's kind of calculate that out. So I'll move the calculator over. Let's see it. I've got 10 negative times 2.2 times 2.2 because it was squared, right? We'll divide that whole thing by 2, all right? And we get a negative 24.2, all right? So d equals negative 24.2 meters. Again, because displacement is a vector quantity, that negative sign is telling us that it's in the down direction, right? And let's try and make some sense about this. We analyze this whole problem from this part here, right? So whatever happened on this side of the problem must be opposite in sign on this part of the problem. So this is negative stuff. That means this was positive stuff. Right? So from the top of the parabola down, it went negative 24.2 meters, which means when it launched, it went a positive 24.2 meters, which we see here. Include your units of measurement, and I hope that helped.